The morning of September 23rd, 1944. 26,000 feet above the Ruhr Valley. First Lieutenant Thomas McKelvey squeezes into a hard banking turn, chasing a Focke-Wulf 190 that's spiraling through the industrial haze below. His P-47 Thunderbolt shudders as 8 50 caliber machine guns spit tracers into empty sky. Every round misses by 70 feet. The German pilot doesn't flinch. He continues his roll, lines up on a straggling B-17, and disappears into a cloud bank before McKelvey can compensate. The lieutenant has just burned through 200 rounds of ammunition and hasn't touched anything except German air. This isn't a failure of courage. This is a failure of physics that no amount of bravery can overcome. And in the autumn of 1944, it's killing American pilots faster than the Luftwaffe ever could. Here's what McKelvey is fighting against. His P-47 is traveling at 420 miles per hour. The Focke-Wulf, he's chasing, is moving at 380 miles per hour in a perpendicular crossing pattern. His 50 caliber rounds leave the gun barrels at 2,800 feet per second. At 400 yards range, those bullets need approximately 0.4 seconds to reach where the target appears to be. But in 0.4 seconds, that Focke-Wulf has moved forward 92 feet. McKelvey's brain, shaped by 400,000 years of human evolution, tells him to aim directly at what he sees. His eyes track the fighter, his hands point the guns at the visible threat, his fingers squeeze the triggers, and every bullet arrives at a point in space the enemy vacated a half-second ago. The mathematics are simple. The execution is impossible. Between March and August 1944, 8th Air Force fighter pilots fired approximately 600,000 rounds per confirmed air victory. 600,000. That's not a measure of poor marksmanship. That's a measure of a fundamental disconnect between human instinct and high-speed aerial combat. American pilots weren't missing because they lacked skill. They were missing because human beings evolved to throw rocks at animals moving at 20 miles per hour, not shoot bullets at machines moving at 400. The problem had been understood theoretically since World War I, when speeds rarely exceeded 120 miles per hour. But by 1944, the Luftwaffe's latest fighters routinely exceeded 400 miles per hour in combat. The deflection angles required to compensate had grown from manageable to catastrophic. A pilot attacking a crossing target at 300 yards needed to aim approximately 40 feet ahead of the aircraft's nose. 40 feet. That's betting everything on empty sky. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The 8th Air Force knew it, had a crisis. Statistical analysis from early 1944 showed that even experienced fighter pilots achieved hit rates below 5% against crossing targets in actual combat conditions. 5%. Major Robert Johnson, already an ace with 17 confirmed kills, estimated that he missed his intended target in 80% of his firing passes. And Johnson was one of the best pilots in the European theatre. The problem wasn't limited to Americans. Royal Air Force pilots had been grappling with deflection shooting since the Battle of Britain in 1940. Detailed analysis of gun camera footage revealed that even Spitfire pilots with 2 years of combat experience consistently undershooted crossing targets by factors of 2 to 3. They saw a Messerschmitt Bf 109 crossing left to right at 300 miles per hour, aimed their guns at the cockpit, fired, and watched every round pass harmlessly behind the tail section. Evolution had prepared human beings to throw a spear at a running antelope. It had not prepared them to fire ballistic projectiles at machines moving 12 times faster than any natural predator. The conscious mind could understand the math. The subconscious reflexes that actually controlled fine motor movements under stress were still calibrated for the African savanna circa 10,000 BCE. Training helped, but only marginally. By mid-1944, American fighter pilots received approximately 40 hours of gunnery instruction before deploying to combat theaters. They practiced against toed sleeve targets moving at controlled speeds in predictable patterns. Under these ideal conditions, competent pilots could achieve hit rates around 20%. Then they arrived in Europe, encountered Luftwaffe fighters moving twice as fast in 3 dimensions, and discovered their training was worse than useless. It had taught them to aim at slow targets. Now they needed to aim at nothing. Captain David Schilling of the 56th Fighter Group spent 3 weeks in July 1944 analyzing gun camera footage from his squadron's missions. He watched frame by frame as his pilots tracked German fighters, positioned their aircraft perfectly, fired at the optimal range, and missed completely. The pattern was consistent. Pilots aimed where the target was, bullets arrived where the target had been, and German pilots flew home untouched. Schilling's report to 8th Air Force Headquarters was brutally direct. Current gunnery doctrine is fundamentally incompatible with combat conditions over Germany. Pilots receive insufficient training in deflection shooting. No standardized method exists for calculating proper lead angles during high-speed engagements. Until we solve the deflection problem, our kill-to-expenditure ratio will remain unacceptable. The British had already been working on a solution since 1939. At the Royal Aircraft Establishment in Farnborough, a small team of engineers led by scientist Leslie Cunningham had been experimenting with something radical. What if the gunsight itself could calculate deflection automatically? What if a gyroscope, spinning independently of the aircraft's movement, could provide a stable reference point and continuously compute where the pilot should aim? The concept was elegant. A gyroscope maintains its orientation in space, regardless of the motion around it. Mount one in an aircraft, connect it to the gunsight's optical system, and the sight could automatically compensate for any aircraft movement. The pilot would see a reticle that adjusted position based on the aircraft's rate of turn. Aim at the moving reticle, and your bullets would intercept the target. The first British prototype, designated the Mark I gyro sight, entered testing in 1941. It was based on a folded prismatic telescopic sight with a single-axis gyroscope. Initial results showed promise. Pilots using the gyro sight achieved hit rates 30 to 40% higher than with conventional reflector sights. But the Mark I had serious problems: limited field of view, erratic reticle behavior, and most critically, it required pilots to press their eye against a narrow eyepiece during violent combat maneuvers. RAF pilots tested it operationally against Luftwaffe raids over Britain in July 1941. Flight Lieutenant Kenneth McGlashan reported that while the sight worked well during straight and level practice runs, it became nearly unusable during actual combat. The narrow field of view meant losing sight of the target during hard maneuvering. The eyepiece smashed into his face during evasive rolls, and the reticle occasionally drifted off-center when the gyroscope couldn't keep up with rapid aircraft movement. Production was postponed. The team at Farnborough went back to work. They needed a sight that combined the gyroscope's automatic computation with the wide field of view and hands-off usability of a standard reflector sight. The solution came from integrating the gyroscope into a reflector system that sat several inches in front of the pilot, rather than requiring direct eye contact. The Mark II gyro sight, tested in late 1943, solved nearly all the Mark I's problems. It projected 2 reticles onto a glass reflector plate. One reticle was fixed, showing where the guns actually pointed. The second reticle, controlled by the gyroscope, moved dynamically to show the correct aiming point. The pilot simply had to adjust the ring size using a throttle-mounted control to match the target's wingspan, which gave the sight the range information it needed. Keep the moving reticle on the target, and the bullets would hit. The transformation was immediate. RAF squadron after squadron reported dramatic improvements in accuracy. Wing Commander James Johnson, already one of Britain's top aces, test flew the Mark II in December 1943, called it, quote, the most significant advance in fighter gunnery since the invention of synchronized machine guns, unquote. His squadron's hit rate against crossing targets tripled within 2 weeks of receiving the new sights. The Mark II used a gyroscope spinning at approximately 7,000 revolutions per minute, powered by a vacuum pump. The gyroscope measured the aircraft's rate of turn in all three axes. That data fed into a mechanical computer that calculated the required lead angle based on the target's range, which the pilot input by adjusting the reticle size to match the target's wingspan. The sight projected the correct aiming point onto the reflector glass. The pilot flew to put that aiming point on the target. Physics handled everything else. American military observers saw demonstrations of the Mark II in early 1944 and immediately recognized its potential. Major General William Kepner, commanding 8th Air Force fighters, cabled Washington with an urgent request. "We need this technology immediately. Every day without gyroscopic gunsights costs us pilots and aircraft we cannot afford to lose. Recommend immediate production of American version for all fighter aircraft." The United States Army Air Forces awarded Sperry Corporation a contract to manufacture American versions of the British sight. The fighter variant would be designated the K-14. The Navy version would be called the Mark 18. Production would begin in July 1944, with deliveries to operational units starting in August. The goal was to equip every American fighter in Europe with the K-14 by the end of the year. The K-14 was mechanically similar to the British Mark II, but included several American modifications. Most notably, it featured two separate projector systems. One system displayed the gyroscopic reticle for air-to-air combat. The second system projected a fixed reticle for ground attack missions, where the gyroscope wasn't needed. This dual-mode capability made the K-14 more versatile than its British predecessor. The sight itself was a marvel of precision engineering. It weighed approximately 6 pounds and contained over 1,000 individual components, many machined to tolerances of 1/10,000th of an inch. The gyroscope assembly alone required 14 precision bearings, all of which had to be perfectly balanced to prevent wobble at 7,000 RPM. The reflector system used specially coated glass that projected a sharp image while remaining virtually transparent to normal vision. Installation in a P-47 Thunderbolt required cutting a recess into the instrument panel combing. The K-14 was significantly larger than the N9 reflector sight it replaced. Armourers at 8th Air Force bases spent a week at specialized schools learning the sight's installation and calibration procedures. One armourer, Technical Sergeant William Hayes of the 362nd Fighter Group, recalled having to use a hacksaw to modify cockpit panels to accommodate the new sight's bulk. The first P-47 units to receive K-14 sights were the 56th and 78th Fighter Groups in early August 1944. Pilots underwent 3 days of ground school, followed by 5 training flights to familiarize themselves with the sight's operation. The learning curve was steep. The K-14 had specific startup and shutdown procedures. The gyroscopes had to spin up for 15 minutes before combat. They had to be caged, locked in place, during violent aerobatic maneuvers to prevent damage. Forget to cage them during a snap roll, and the entire sight could be destroyed. But once pilots mastered the procedures, the results were extraordinary. Captain Walker Mahurin of the 56th Fighter Group flew his first combat mission with the K-14 on August 15, 1944. He engaged 2 Focke-Wulf 190s at 18,000 feet over Belgium. Both German fighters were crossing at high speed, the exact scenario where deflection shooting was most difficult. Mahurin adjusted his throttle grip to match the target wingspan, placed the moving reticle on the lead fighter, and pressed his gun triggers. His after-action report was succinct. First burst, strikes observed on fuselage and left wing. Target rolled inverted and entered uncontrolled dive. Engaged second fighter, similar crossing angle. Second burst, strikes on engine cowling. Heavy smoke, confirmed, destroyed. Total ammunition expenditure, approximately 400 rounds for 2 kills. Previous combat average for similar engagements, 3,000 rounds. The 8th Air Force Statistical Office began tracking K-14 effectiveness in September 1944. Initial data showed pilots equipped with the gyroscopic sight achieving hit rates between 15 and 25% against crossing targets, compared to historical rates of 3 to 5% with conventional sights. The improvement wasn't just incremental, it was transformational. Pilots who had struggled for months to score kills were suddenly shooting down German fighters on their first pass. Lieutenant Colonel Francis Gabreski, America's top P-47 ace with 28 confirmed victories, received his K-14 inches early September after returning from a stint as a prisoner of war. He told his squadron that the sight represented, quote, "the difference between hoping you hit something and knowing you will," unquote. Combat veterans who had learned deflection shooting through brutal trial and error found the K-14 vindicated everything they'd taught themselves. The sight was doing automatically what they'd spent months learning to do through instinct and experience. On September 7, 1944, a P-47 Thunderbolt from the 355th Fighter Group made an emergency landing near Aachen after taking flak damage to its oil system. Second Lieutenant William Roach had been escorting bombers deep into Germany when anti-aircraft fire severed a hydraulic line. With his engine seizing and altitude bleeding away, he had no choice. He put the wounded Thunderbolt down on what appeared to be an abandoned airfield. It wasn't abandoned. It was Luftwaffe fighter base Langerbehe, home to Jagdgeschwader 26. German ground crews swarmed the aircraft within minutes. Roach was captured and sent to Stalag Luft 1. His P-47, tail number 42-75908, was carefully examined by Luftwaffe technical intelligence officers, who had been waiting months for exactly this opportunity. They were particularly interested in the device mounted just forward of the instrument panel, the K-14 gyroscopic gunsight. German intelligence had known since early summer that American fighters were being equipped with some form of advanced sighting system. Luftwaffe pilots had reported that American accuracy seemed to be improving dramatically. Crossing attacks that should have been safe now resulted in immediate, devastating fire. But until September, the Germans hadn't been able to examine the actual hardware. Oberst Josef Priller, commander of Jagdgeschwader 26 and a veteran with over 100 victories, filed a priority report to the Reich Air Ministry. The Americans have fielded a gyroscopic computing sight far more advanced than our current REVI reflector system. This device automatically calculates deflection based on aircraft turn rate and target range. It represents a significant tactical advantage that explains recent increases in American gunnery effectiveness. The captured K-14 was transported to the Rechlin aircraft testing facility northeast of Berlin. There, Luftwaffe engineers disassembled it component by component. What they found was both impressive and concerning. The sight's gyroscope assembly was smaller and more reliable than comparable German prototypes. The mechanical computer that calculated lead angles was elegantly designed, and the dual reticle system that showed both fixed and computed aiming points was far superior to anything in German service. German engineers had actually been working on gyroscopic gun sights since 1935. The Carl Zeiss and Askania companies had both submitted prototypes, designated the EZ 40 inches the late 1930s, but development had proceeded at low priority. The standard REVI reflector sight, though primitive, worked adequately against slower targets, and gyroscopic systems were complex, expensive, and difficult to manufacture in quantity. The situation changed in 1942 when the Luftwaffe realized that Allied fighters were becoming faster and more maneuverable. The Reich Air Ministry accelerated development of the EZ-42, an advanced gyroscopic sight that Askania had been designing. But progress was slow. Prototype testing didn't begin until mid-1943. The first production units weren't delivered until July 1944, just 33 examples. By the time the Germans captured Roach's P-47 inches, September, they were approximately 18 months behind the British and Americans in fielding operational gyroscopic gun sights. The gap was widening. Sperry Corporation was producing hundreds of K-14 sights per month. Ascania, working in facilities constantly disrupted by Allied bombing, was struggling to build dozens. The industrial capacity that had given America its advantage in heavy bombers and long-range fighters was now extending to precision optical instruments. But the Germans did complete their testing of the captured K-14. In late September 1944, Rechlin engineers installed both the K-14 and a German EZ-42 prototype in the same Focke-Wulf 190. The same test pilot flew both sites under controlled conditions. The comparison was methodical and detailed, and the results were surprising. The German report, declassified decades later, was critical of the K-14 inch's several respects. The moving reticle could be obscured by the target aircraft at close range. The K-14's prediction angle was on average 20% less accurate than the EZ-42. Tracking stability was inferior to the German sight. German engineers concluded their own design was technically superior. The Royal Aircraft Establishment later assessed these findings and noted they were, quote, of doubtful validity, unquote. The test methodology was inadequate. The German system would suffer considerable altitude and temperature sensitivity problems in actual combat. And critically, the British were very critical of the extremely simple training offered on usage of the sights. The Germans had tested the K-14 without fully understanding how to operate it properly. But even if the EZ-42 was technically superior on paper, it didn't matter. Technical excellence means nothing if you can't manufacture and deploy the technology at scale. By December 1944, approximately 3,000 K-14 sites were in service with American fighter squadrons in Europe. The Luftwaffe had fielded fewer than 200 EZ-42 units, mostly for field testing in Me-262 jet fighters and late-model F-Turbluff U-192s. The fundamental issue wasn't engineering capability. It was industrial capacity. Germany's precision manufacturing infrastructure was being systematically destroyed by around-the-clock Allied bombing. The Steinheil optical factory in Munich, which produced the EZ-42, required 130 labor hours to build each site. And that was assuming the factory had consistent electrical power, raw materials, and a workforce that wasn't being conscripted or killed in air raids. America's Sperry plants in New York operated 24 hours a day with unlimited electrical power, abundant raw materials, and a workforce of skilled technicians who went home to safe neighborhoods every night. The gap wasn't just technological, it was civilizational. The country with intact factories produces weapons. The country with burning cities produces statistics. By November 1944, the majority of 8th Air Force P-47 units had transitioned to the K-14. The 56th Fighter Group, the 78th, the 353rd, the 356th, all received the new sights as aircraft underwent routine maintenance. Pilots who had struggled for months against the deflection problem suddenly found themselves consistently hitting crossing targets. The transformation in combat effectiveness was measurable and immediate. Major Gerald Johnson of the 56th Fighter Group achieved 6 confirmed victories in October 1944 alone, all using the K-14. His average ammunition expenditure dropped to 600 rounds per kill, down from over 2,000 rounds earlier in the year. When asked about the difference, Johnson said, quote, "Before the K-14, I was guessing. Now I'm computing. The Germans can't tell the difference from their cockpit, but I can tell from mine," unquote. The psychological impact was equally significant. Pilots gained confidence. They knew that if they could get into firing position and properly track the target, the sight would handle the mathematics. This confidence translated into more aggressive tactics. P-47 pilots began engaging multiple targets in single missions, knowing they had the ammunition efficiency to take calculated risks. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Luftwaffe pilot reports from late 1944 increasingly mentioned that American fighters were more willing to engage in turning fights rather than relying exclusively on dive and zoom attacks. Major Heinz Baer, a Luftwaffe ace with over 200 victories, was shot down by a P-47 on November 3, 1944. After the war, he commented that American gunnery had become, quote, disturbingly accurate, unquote. In the final months of the gunnery, conflict. But the real revolution wasn't just accuracy, it was accessibility. The K-14 democratized deflection shooting. Before gyroscopic sights, hitting a crossing target required either natural talent honed by extensive combat experience or months of dedicated practice. Aces like Robert Johnson and Francis Gabreski had that combination of talent and experience. Average pilots didn't. The K-14 compressed the learning curve from months to days. Technical Sergeant James Morrison, a newly deployed pilot with the 361st Fighter Group, scored his first aerial victory on his second combat mission in December 1944. A Messerschmitt Bf 109 crossed his flight path at 400 yards. Morrison adjusted the throttle grip, matched the reticle to the target's wingspan, placed the computed aiming point on the enemy cockpit, and fired. The 109 disintegrated under a 5-second burst. Morrison had been in combat for exactly 9 days. Under the old system, Morrison would have needed 10 or 15 missions to develop the instinctive feel for deflection shooting. Some pilots never developed it at all and washed out of combat duty. The K-14 didn't eliminate the need for piloting skill, tactical awareness, or courage under fire. But it eliminated one of the most difficult technical barriers to aerial combat effectiveness. The sight's impact extended beyond individual duels. Fighter groups equipped with K-14 sights could more effectively protect bomber formations. Every fighter that could reliably hit crossing targets was a fighter that could disrupt German attack runs before they reached the bombers. The 8th Air Force's bomber loss rates began declining in late 1944. Part of that decline was due to reduced Luftwaffe strength, but part was due to more effective fighter escorts, equipped with better sights. The P-47 Thunderbolt proved an ideal platform for the K-14. The aircraft's exceptional stability at high speed meant that pilots could hold the computed aiming point steady during firing runs. The P-47's 850 caliber machine guns, synchronized to converge at 300 yards, created a concentrated cone of fire. With the K-14 properly employed, that cone arrived exactly where the pilot intended. Captain David Schilling, who had written the critical report on deflection shooting back in July, flew with the K-14 throughout the autumn of 1944. His kill tally climbed steadily. By December, he had achieved 22 confirmed victories, most during the period when he was using the gyroscopic sight. Schilling's assessment was unequivocal. The K-14 represents the single most important advance in fighter effectiveness since the adoption of the synchronized machine gun. It transforms aerial combat from an art form practiced by talented individuals into a repeatable technical process, accessible to competent pilots. Not every pilot loved the K-14. Some veterans preferred the simplicity of the old N9, the reflector sight, and relied on their developed instincts for deflection shooting. Major Walker Mahurin occasionally switched back to fixed reticle mode during ground attack missions where the gyroscope wasn't needed. And some pilots found the K-14's startup procedures annoying, particularly the requirement to power up the gyroscopes 15 minutes before combat. But the statistics didn't lie. By January 1945, 8th Air Force fighter groups using the K-14 were achieving kill-to-loss ratios above 4-1 against Luftwaffe fighters. Previous ratios had hovered around 2-1. The improvement wasn't solely due to the gunsight. German pilot quality was declining as experienced veterans were killed and replaced by hastily trained recruits. But the K-14 ensured that American advantages in training and equipment translated into combat effectiveness. The Pacific Theater received K-14 sights more slowly than Europe. Logistics challenges meant that many P-47 units in the rived Southwest Pacific continued using N9 sights well into early 1945, but those units that did receive the K-14 reported similar improvements. The 5th Air Force, operating P-47 seconds over the Philippines, reported hit rates against Japanese fighters improved from approximately 5% to 18% after K-14 installation. The site's ground attack mode proved valuable in the Pacific. The fixed reticle could be used for strafing runs against ships, airfields, and ground targets without the complexity of the gyroscopic system. Pilots appreciated having both modes available in a single integrated sight. Captain Thomas Maguire of the 5th Air Force used his K-14 to destroy 3 Japanese fighters and strafe 2 airfields in a single mission over Luzon in December 1944. But it was in Europe where the K-14 had its greatest impact. The air war over Germany in late 1944 was brutal and unforgiving. Luftwaffe pilots were defending their homeland with the desperation of men who knew they were losing. They flew tactics designed to maximize casualties among American bombers and their escorts. Every advantage mattered. Every percentage point of improved accuracy translated into American pilots who came home alive. First Lieutenant Thomas McKelvey, the pilot who opened this story by missing a Focke-Wulf over the Ruhr Valley in September, received his K-14 inches early October. He flew his first mission with the new sight on October 9, 1944. The target was Nuremberg. The Luftwaffe intercepted in force. McKelvey engaged a Messerschmitt 109 inches, a hard left turn at 19,000 feet. He adjusted the throttle grip, matched the diamonds to the target wingspan, placed the computed reticle on the enemy cockpit, and fired a 3-second burst. His after-action report noted that approximately 30 rounds struck the target's engine and left wing root. The Messerschmitt rolled inverted, caught fire, and the pilot bailed out at 15,000 feet. McKelvey had expended perhaps 100 rounds. 4 weeks earlier, he'd burned 200 rounds and hit nothing. The difference wasn't courage or determination. The difference was a spinning gyroscope and mechanical computer that solved differential equations faster than any human brain. The K-14 didn't win the war. No single technology wins wars. Wars are won by industrial capacity, strategic vision, trained personnel, and the moral courage to see difficult things through to completion. But the K-14 exemplified America's approach to technological warfare. Identify a problem, engineer a solution, manufacture at scale, deploy rapidly. The British invented the gyroscopic gunsight. The Americans turned it into an industrial product and put thousands into combat in 6 months. German pilots in late 1944 found themselves fighting enemies who could see at night using airborne radar, navigate precisely using radio beacons, and now hit crossing targets with mechanical precision using gyroscopic computers. Each advantage was small. Collectively, they were insurmountable. The Luftwaffe was flying excellent aircraft piloted by brave men, but bravery without technological parity is just elaborate suicide. By the end of 1944, the questions weren't whether Germany would lose the air war. That was decided. The questions were how long the killing would continue and how many would die before it ended. American fighter pilots, equipped with K-14 sights, could at least fight with the confidence that their weapons would perform as designed. They could aim at a moving target 400 yards away, trust the gyroscope and mechanical computer to calculate the interception point, and know that physics would deliver their bullets precisely where intended. The winter of 1944 through 45 was the coldest in Europe in 50 years. At 25,000 feet above Germany, temperatures dropped to -50 degrees Fahrenheit. Hydraulic fluid thickened. Oxygen masks froze to pilots' faces. And the K-14 gyroscopic gunsights, with their precision-machined components and delicate gyroscope bearings, had to function flawlessly in conditions that would destroy most mechanical instruments. They did. The K-14's engineering specifications required operation from -40 to +120 degrees Fahrenheit. Sperry engineers had tested the sights in environmental chambers that simulated the worst conditions pilots would encounter. The gyroscope bearings were lubricated with special low-temperature grease that remained fluid at extreme cold. The electrical components were sealed against moisture. The result was a sight that functioned as reliably at -50 degrees as it did in the warmth of a maintenance hangar. Captain Robert Johnson of the 56th Fighter Group flew through some of the worst weather of the war in January 1945. On a mission to Cologne on January 14th, his P-47 encountered icing conditions so severe that frost accumulated on the inside of his canopy. The temperature gauge read -48 degrees. Johnson engaged two Focke-Wulf 190s at 23,000 feet, his hands so cold he could barely feel the controls. The K-14 functioned perfectly. Both German fighters went down. Johnson's hands were frostbitten, but the gyroscope kept spinning at 7,000 revolutions per minute as if it were a summer afternoon. The sight's reliability became legendary among pilots who depended on it. Technical failures were rare, usually caused by improper maintenance or damage from flak rather than design defects. Armourers learned to treat the K-14 with respect. Calibration checks before each mission. Careful cleaning of the reflector glass. Verification that the gyroscope spun up properly during pre-flight. Pilots who maintained their sights properly could fly dozens of missions without mechanical issues. But the K-14 couldn't solve every problem. It required the pilot to manually estimate target wingspan and adjust the ranging dial accordingly. Get the wingspan wrong, and the computed lead angle would be incorrect. Misidentify a Focke-Wulf 190 as a Messerschmitt 109, input the wrong wingspan, and your bullets would miss by 20 feet despite the gyroscope's perfect calculations. The sight was a tool, not magic. It computed answers based on the data it received. Garbage in, garbage out. Experienced pilots learned the silhouettes and dimensions of every Luftwaffe fighter by heart. Messerschmitt 109, wingspan 32 feet. Focke-Wulf 190, wingspan 34 feet. Messerschmitt 262 jet, wingspan 40 feet. Get those numbers wrong, and the most advanced gunsight in the world became just an expensive paperweight. Training programs emphasized aircraft recognition until pilots could identify targets at a glance under any conditions. The jet problem became significant in late 1944. The Messerschmitt 262 was the world's first operational jet fighter, with a top speed exceeding 540 miles per hour. When Me-262 seconds began intercepting bomber formations in significant numbers in November, American pilots discovered that deflection angles for jet targets were far larger than for conventional fighters. A 262 crossing at 400 yards required a lead of nearly 60 feet. The K-14 could calculate it, but only if the pilot correctly input the 40-foot wingspan and accurately tracked a target moving 50% faster than anything they'd encountered before. Lieutenant Colonel John Meyer of the 352nd Fighter Group achieved one of the first American victories over an Me-262 using a K-14 sight. The date was October 7, 1944. Meyer intercepted two jets attacking bombers over Akme. The jets were fast, but they had to slow down to attack the bombers. Meyer rolled in behind one as it completed its firing pass. He set his ranging dial for what he estimated was a 40-foot wingspan, tracked the jet through a slight left turn, and fired when the computed reticle lined up. The burst struck the Me-262's right engine. The jet caught fire and the pilot ejected. Meyer had just demonstrated that even the Luftwaffe's most advanced fighter could be defeated by a properly employed K-14 and a pilot who understood his tools. The arrival of the P-51 Mustang in large numbers created some operational complexity. Mustangs were also being equipped with K-14 sights, and P-47 pilots had to be absolutely certain of target identification before firing. The last thing anyone wanted was to shoot down a friendly fighter because they misidentified it in the confusion of combat. Friend or foe recognition became critical. P-47 seconds and P-51 seconds flew different profiles and operated in different areas when possible. Radio discipline improved. And gun camera footage reviews became mandatory to verify kills and prevent friendly fire incidents. By February 1945, the tactical situation over Germany had shifted decisively in favor of the Allies. The Luftwaffe was running out of fuel, pilots, and functioning airfields. Many German fighters couldn't take off because Allied bombing had destroyed fuel depots and transportation networks. When they did fly, they encountered American fighters that outnumbered them 5-1 and were equipped with technology that gave them significant advantages in any engagement. The kill ratios reflected this dominance. In March 1945, 8th Air Force fighters achieved overall kill ratios exceeding 6-1. P-47 units equipped with K-14 sights reported ratios as high as 8-1 during the final weeks of the war. These numbers represented not just technological superiority, but complete air supremacy. German pilots were fighting with obsolete tactics, inadequate training, and insufficient numbers against an enemy that controlled every aspect of the air battle. But individual German pilots could still be lethal. On March 2, 1945, Major George Preddy, America's top P-51 ace with 26 confirmed kills, was shot down by friendly fire from American anti-aircraft gunners who misidentified his aircraft. The incident highlighted that technology and training couldn't eliminate every danger. Mistakes still happened. Men still died. The K-14 made deflection shooting reliable, but it couldn't protect pilots from ground fire, mechanical failures, or tragic errors in identification. The final weeks of the war in Europe saw diminishing aerial combat. The Luftwaffe had been reduced to scattered remnants flying sporadic missions with dwindling fuel supplies. P-47 units transitioned increasingly to ground attack missions, using their 850 caliber machine guns and bomb loads to destroy German armor and vehicles. The K-14's ground attack mode proved valuable for these missions, though the gyroscopic system wasn't needed for strafing runs. Victory in Europe came on May 8, 1945. By that date, approximately 6,000 K-14 sights had been fielded to American fighter units in Europe and the Pacific. The exact impact on the war's outcome is impossible to quantify precisely, but the statistics provide strong evidence of effectiveness. Fighter groups using K-14 sights achieved measurably higher kill ratios and lower ammunition expenditure rates compared to units using conventional sights. After the war, military analysts attempted to calculate the K-14's contribution to Allied victory. The consensus was that the sight had improved American fighter effectiveness by approximately 30 to 40% in air-to-air engagements. That improvement translated into hundreds of additional German aircraft destroyed, thousands of rounds of ammunition saved, and an unknown but significant number of American pilots who survived missions they might otherwise have lost. The mathematics of warfare are cruel. A 30% improvement in effectiveness means 30% more enemies destroyed or 30% fewer friends killed. Usually both. The legacy of the K-14 extended far beyond World War II. The principles it embodied, gyroscopic stabilization and automated ballistic computation, became fundamental to every guided weapons system developed afterward. The Korean War's F-86 Sabre jets used the A-4 radar-ranging gunsight, which combined the K-14's gyroscopic system with radar to automatically measure target distance. The pilot no longer had to estimate wingspan. The radar did it instantly and precisely. Modern fighter aircraft use systems that would seem like science fiction to Thomas McKelvey or Robert Johnson. The F-22 Raptor's fire control computer integrates data from radar, infrared sensors, and inertial navigation systems to calculate firing solutions automatically. The pilot designates a target. The computer determines lead angle, range, closure rate, and a dozen other variables. The pilot presses the trigger, and physics delivers 20mm rounds exactly where intended, but the fundamental problem remains identical. A bullet or missile travels at finite speed toward a target moving in 3 dimensions. Hitting that target requires computing the interception point where projectile and target occupy the same space at the same time. The K-14 solved that problem mechanically in 1944, Modern fighters solve it electronically in the 21st century. The technology has evolved. The physics haven't changed. The P-47 Thunderbolt ended World War II with an impressive combat record. Over 7,000 enemy aircraft destroyed, more than half in air-to-air combat. A kill-to-loss ratio of 4.6 to 1. And only 3,499 P-47 seconds lost to all causes in over 746,000 combat sorties. That represents a loss rate of 0.4 to 7% per mission. For a large, heavy fighter operating in the most intense air combat in human history, those are remarkable statistics. How much of that success was due to the K-14? Impossible to say with precision. The P-47 was a superb aircraft, rugged and powerful. American pilots were well trained and motivated. Tactics improved throughout the war. And by late 1944, the Luftwaffe was fighting with diminishing resources against overwhelming opposition. But every P-47 pilot who used the K-14 combat credited it with making them more effective. And the statistical evidence supports their assessment. Carl Norden, the engineer who pioneered gyroscopic stabilization for his famous bomb sight, never saw the K-14. He was focused entirely on precision bombing, not aerial gunnery. But the principles he proved with the Norden bomb sight, that gyroscopes could provide stable reference platforms for weapons guidance, influenced every subsequent development in fire control technology. The K-14's designers at Sperry and Ferranti built on foundations that Norden and others had established. First Lieutenant Thomas McKelvey, who missed that Focke-Wulf over the Ruhr in September 1944, survived the war. He flew 43 combat missions with the 355th Fighter Group and was credited with 4 confirmed victories, all achieved after he received his K-14 October. He returned to Ohio in June 1945, married his high school sweetheart, and worked as an engineer for General Electric for 37 years. He rarely spoke about the war, but when asked about the K-14 a 1988 interview, he said simply, quote, "That sight saved my life. I know it did. Before the K-14, I was a mediocre shooter hoping to get lucky. After the K-14, I knew that if I did my job right, the sight would handle the rest." Unquote. The K-14 represents a particular moment in technological history, when mechanical computers built from gears and gyroscopes could solve problems that human reflexes couldn't handle. That moment lasted perhaps 30 years, from the 1940s through the 1970s, before digital computers replaced mechanical calculators. But during that window, instruments like the K-14 demonstrated that humans could extend their capabilities through carefully engineered tools that compensated for biological limitations. Evolution shaped human brains to throw rocks at prey, moving at running speed. It did not shape them to shoot bullets at aircraft moving at 400 miles per hour. The conscious mind understands the physics. The subconscious reflexes that control fine motor movements under stress do not. The K-14 bridged that gap. It allowed pilots to use their conscious understanding of deflection shooting to override their instinctive impulse to aim directly at visible targets. The sight computed, the pilot trusted, and physics delivered the bullets to the interception point. This capability, trusting computational aids over instinct, may be one of humanity's defining characteristics. We are the species that builds tools to overcome our evolutionary constraints. We can't fly, so we build aircraft. We can't compute ballistic trajectories instinctively, so we build mechanical computers that can. We extend our senses with radar and infrared. We amplify our strength with engines and hydraulics. And we compensate for our limitations with instruments that handle tasks evolution never prepared us for. The pilots who flew P-47 seconds over Germany in 1944 and 45 were ordinary young men, average age 23, thrust into extraordinary circumstances. They learned to fly machines that could kill them through a moment's inattention. They navigated across hostile territory using instruments and dead reckoning. They fought enemies who were trying to kill them while they tried to kill those enemies first. and they trusted gyroscopes and mechanical computers to solve mathematical problems their brains couldn't handle under combat stress. That trust, the willingness to aim at empty sky because physics and mathematics insist that's where the target will be, represents intellectual courage of a high order. Every combat pilot who used the K-14 successfully had to suppress every instinct screaming at them to aim at the visible threat. They had to fire at nothing while death approached at 400 miles per hour, and they had to believe that the spinning gyroscope in the instrument panel understood trajectories better than their eyes and hands did. They were right to trust it. The K-14 worked. The mathematics were sound, the engineering was solid, and the results validated the trust that pilots placed in technology they didn't fully understand but learned to rely upon completely. This relationship, humans trusting machines to handle tasks beyond human capability, has become foundational to modern life. We trust autopilots to fly aircraft. We trust computers to navigate cars. We trust algorithms to make split-second decisions in circumstances too complex for human processing. The K-14 gyroscopic gunsight was an early example of this partnership. Not the first, certainly, but one that operated under conditions where failure meant death and success meant survival. The pilots who used it successfully demonstrated that humans can adapt to technologies that require counterintuitive actions based on abstract principles rather than direct observation. This adaptability may be our species' greatest survival trait. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Germans never expected gyroscopic gunsights to make P-47 pilots hit targets at 400 miles per hour. They understood the theory. They'd been working on similar technology since 1935. But they couldn't manufacture and deploy it at scale during a total war that was destroying their industrial capacity. The Americans could, and that made all the difference. Not because American engineers were smarter, but because American factories kept running while German factories burned. Technology wins battles, industry wins wars. And in the winter of 1944, American industry delivered a spinning gyroscope that transformed ordinary pilots into precise instruments of aerial warfare. The P-47 Thunderbolt gave them the platform, the K-14 gave them the precision, and together they gave the Allies supremacy in the skies over Europe when it mattered most.